Jai Shri Ram friends, welcome to my channel. Now, today's lecture number 9, we shall talk about superposition concept, the electric field and some numerical problems we shall see. Let us start. What is superposition principle? The superposition principle states that when a number of charges are interacting, the total force on a given charge is the vector sum of the forces exerted on it due to the other charges. As you can see in this diagram, there are different charges, Q1, Q2, Q3, etc. There are different forces. Okay, the F1, for instance, is nothing but equal to F2 plus F3. So the important point to note is that the force between two charges is not affected by the presence of other charges. Now, see one numerical question. Consider the charges Q, Q, and minus Q placed at the vertices of an equilateral triangle as shown in the figure. This what is the force on each charge? Now, you can see in this diagram. See, this is the equilateral triangle. So each force has magnitude F is equal to 1 upon 4 pi epsilon naught Q square upon L square because the edge length is L. Now, by parallelogram law, you can say that F this vector is nothing but under root F square plus 2F into F cos 120 into BC direction. Okay, what is BC? BC cap means in the direction of B to C, like this. B to C. B to C's direction, this one. These one, right? This is BC cap. Similarly, we can find out F1 magnitude, that is equal to F into BC. So BC is the unit vector along BC. Similarly, force on Q2. Q2 is this one, right? So F2 is equal to F into AC because this is a equilateral triangle. And as per the symmetry, the F2 would be same as this F1. Now total force on a Q3 is nothing but F3, as you can see in this diagram. Now this is since minus charge, so therefore this would be a little bit different. So that comes out to be under root 3 F into N. So where N is the unit vector along the bisector of ACB. So this is the final answer. Next is what is electric field? Electric field at a point is defined as the electrostatic force per unit test charge acting on a vanishingly small, that is very small positive charge placed at that point. Okay, suppose this is a diagram which shows the source charge and test charge. Okay, then E is equal to means is the vector quantity, that is vector F1 Q0, or you can say E vector is equal to limit Q0 tends to 0 F vector on Q0. So Q0 is vanishingly small. So electric field E is a vector quantity whose direction is same as that of the force F exerted on a positive charge test charge. Okay, now electric field due to a point charge. How to calculate? Suppose this in this diagram there is a charge, source charge, and there is a test charge, and there is a force exerted on test charge due to the source charge at a distance of L. So where this R is a position vector. So you can say force on Q0 is equal to F vector is equal to 1 upon 4 pi epsilon naught Q0 upon R square into R cap. So electric field due to Q is nothing but F upon Q. So you can say E vector is equal to 1 upon 4 pi epsilon naught Q upon R square in the direction of R cap. Right now, magnitude, if you want to calculate, how to calculate the magnitude? The magnitude is nothing but E is equal to 1 upon 4 epsilon naught Q upon R square. So E is proportional to 1 upon R square, means inversely proportional to the distance, the square of the distance. So this is physically symmetrical for radial electric field due to the point charge. Electric field due to a system of point charges. Now, if there are a number of point charges, then what shall we do? In that case, the electric field at any point due to a group of charges is equal to the vector sum of the electric field produced by each charge individually at that point when all other charges are assumed to be absent, right? So this is a kind of superposition principle. So you can say this as per this diagram, the electric field at point P due to the system of n charges, that is E vector is equal to E1 vector plus E2 vector plus En up to En vector. Okay. Now see another problem to illustrate the superposition principle. 2 point charges plus 16 microcoulomb and minus 9 microcoulomb placed at 8 centimeter apart in the air. Determine the position of the point at which the resultant field is 0. See, this is the diagram illustrating this language of the question. Okay, plus 16 and this is minus 16. Suppose the point P is somewhere between A and B, that is the distance of x from A. So this would be 8 minus x because the whole distance is there 8. So at point P, E1 plus E2 is equal to 0. So you can say field this E1 is nothing but K, that is 1 upon 4 epsilon naught 16 into 10 to the power minus 6 divided by x into 10 to the power minus 2 whole square. Okay, plus E2 is equal to K into minus 9 because this is minus. So minus 9 into 10 to the power minus 6 upon 8 minus x because distance of P from B is 8 minus x. So you can say into 10 to the power minus 2 whole square. That should be equal to 0. So if you are solving this, you are getting the x of x as two values. Number one is 32 by 7 centimeter, another is 32 centimeter. Now see the magic here. The thing is at x is equal to 32 by 7 centimeter, that is 4.57 centimeter. Both E1 and E2 will be in the same direction. So E net is not equal to 0. Okay, so that value shall be discarded. And hence we shall take x is equal to 32 centimeter, that is electric field is 0 at a point that is 32 centimeter to the right of plus 16 microcoulomb. So the correct answer is this, the 32 centimeter. Now electric lines of force. What are electric lines of force? Suppose in this direction, an electric line of force may be defined as the curve along which a small positive charge would tend to move when free to do so in an electric field, and the tangent to which at any point gives the direction of the electric field at that point. Okay, so here the point to be noted is the lines of force do not really exist. They are imaginary curves, yet the concept of lines, basically line of force, is useful to solve the problems. Okay, now there are different properties of electric lines of force. So let us do one by one. First one is the line of forces are continuous smooth curves without any breaks. Second, the line of force start at positive charge and end at negative charges. They cannot form closed loops. So if there is a single charge, then the line of force will start or end at infinity. Third point is the tangent to a line of force at any point gives the direction of the electric field at that point. Similarly, fourth point is no two lines of force can cross each other. Okay, in this direction we can see this. Okay, the reason is that if they intersect, then there will be two tangents at the point of intersection as shown in the figure, and hence two directions of the electric field at that same point, which is not possible. Okay. Next point is the line of forces are always normal to the surface of the conductor on which the charges are included. इसका रीजन क्या है कि if the lines of forces are not normal to the conductor, the component of field which is parallel to the surface would cause the electrons to move and would set up a current on the surface, but no current flows in the equilibrium condition. Now, next point is the lines of force have a tendency to contract lengthwise. This explains the attraction between the two unlike charges. Seventh point is the lines of forces have a tendency to expand laterally so as to exert a lateral pressure on the neighboring lines of force. This explains the repulsion between the two similar charges. Okay. Now, next point is, which is the eighth point, the relative closeness of the lines of force gives a measure of the strength of the electric field in any region. The line of forces are, number one, the close together in the strong field, far apart in the weak field, and parallel and equally spaced in the uniform field. Okay. And ninth point is the lines of forces do not pass through a conductor because the electric field inside a charged conductor is zero. Okay. Now, electric field lines for different charged conductors. So we shall see one by one. These are two different types of charges, positive and negative. So field lines of a positive point charge, you can say this is radially outward or inward, you can say. So field lines are of a positive point charge. Number one, radially outward, as you can see in this. They extend to infinity and the field is spherically symmetric. For negative charge, what is happening? The field is again radially but inwards, and they start from infinity, okay, and spherically symmetric. So these are two different types. Now, field lines for equal and opposite charges. Suppose a kind of dipole structure is there. So this is positive and this is one is negative. Okay, so the two charges are placed side by side. So the field is cylindrically symmetric about the dipole axis. You can see from this. Okay, this dotted line shows the dipole axis. Okay, next point is the field lines for equal and positive charges. इसमें क्या होगा? The field E0 at the middle point and of the join of the two charges. This point is called neutral point, from which no line of force passes. As you can see, so at this point, neutral point, the field is zero. So no force, line force is passing through this. So this field has also cylindrical symmetry. Okay, so this is about the lines of forces. Again, electric field lines for charged parallel conductor. इसमें कैसे दिखाएंगे? तो they are equispaced, indicating that the electric field E is uniform at all points near the plane conductor, as you can see in this diagram. Okay. Thus, the lines of forces are parallel and normal to the surface of the conductor. Okay. Now, the relation between electric field strength and density of lines of force. So, electric field strength is proportional to the density of lines of force. Okay. As you can see in this diagram, density of lines of force is proportional to the electric field strength. Okay. यहाँ पर देखिए पास पास है और यहाँ पर दूर हो गई है. So, region of this is weak field. This here the field is weak, but here the field is strong. Okay. So, high density means high electric field and low density means low electric field. Okay. For instance, I am just showing this. This diagram shows that there is a conductor. So, there are three different ways to the show the path of the field lines. So number one path is wrong, similarly number two is wrong, but number three is correct because the electric field lines incident at normal to the surface. Okay, so this shows the normal incident. Similarly, they move out because they are radially outward or inward. So this is conductor in electric field. Similarly, parallel plate conductor से अगर फील्ड निकलेगी तो इस तरीके से आपकी फील्ड्स निकल लेंगे. Okay, so if we are placing a conductor near a parallel plate, okay, so the field direction will be like this. So this is basically the direction of different field lines and different properties. So this is all about today's lecture, friends, and we shall discuss the next lecture, other topics. Till then, Jai Shri Ram.